Just before the break, we were looking at the constant velocity and constant acceleration models and how they differ in the quality of the approximation that they provide to the underlying physics. Now we're going to just consider some more mechanics topics, and it's mainly momentum and energy, and look at how these can be used to solve some basic mechanics type problems as well. Okay. So there's a little section here on force and acceleration. I think I'm gonna mostly skip over this. This is just giving some basics, kind of the basic ideas of Newtonian physics and the way they relate forces, or kind of give you the equivalence between forces and the accelerations that they produce. And force and acceleration are related through this famous relationship: force equals mass times acceleration. So that holds in the vector setting as well. So the force, the vector representing a force in 3 dimensions is equal to, well, if it's acting on an object, then the effect it produces in the object is to produce an acceleration such that the magnitude of the acceleration is 1 over the mass times the magnitude of the force. And the acceleration is going in the same direction as the force applied. So maybe just to illustrate the use of those, we'll have a look at this exercise here, exercise 8.7. So just do this work on the screen again. So we're looking at exercise 8.7. So here we're dealing with a rocket of a certain mass, 8,000 kilograms, moving through space with a certain initial velocity. So we're given an initial velocity value here of u, which is 100. Again, it's a 3-dimensional vector quantity, 100, 50, 10. This velocity, so this is meters per second. And its motor is fired for 10 seconds. Now the motor generates a force of 10,000 newtons. The newtons is the units of force, and those in meters and seconds and kilograms. That's kilograms, kilogram meters per second. It's the magnitude of force. But we'll take it that the force vector is this 3-dimensional vector. So the magnitude of this force vector is 10,000. The magnitude of that 3-dimensional vector is 10,000. And this force is being applied for 10 seconds. So what will the position and velocity of the rocket be at the end of the rocket burn? Okay, so we need to find the acceleration. And the acceleration A will be given as 1 over the mass times the force. Okay. So this is 1 over the mass of the object, which is 8 tons, 8,000 kilograms, times this force vector, 4970, 8190, times 2870. And well, I've calculated that beforehand, so this comes out as approximately, maybe exactly 0.62125, 1.02375, just evaluating this, minus 0.35875. Okay, so this is the acceleration. This is the acceleration produced on the ship. So although the force is huge, I mean the force is 10,000 newtons, but the ship is very massive. The ship is 8 tons. So compared to the magnitude of the force, it's in some sense, a relatively modest acceleration vector produced because the mass of the ship is so great. Right? The more massive an object, the more of a force it takes to produce any given acceleration. So now we have the acceleration vector. We can feed this into our normal time equation. So the displacement of the ship. So vector s of the ship then will be given by take one of our equations. So we can have the initial velocity times t plus a half of at squared. So this was, remember we had a few different equations for s. This is the one using initial velocity plus half the acceleration times t squared. And we have vectors u and t, so we can easily calculate vector s. So the initial velocity was 115.10, where the question says over a period of 10 seconds. So the rocket is firing for 10 seconds. So then you've got a half of the acceleration vector, 0.6, 1.0, minus 0.35, that vector times t squared, so just times 100. And this comes out approximately 1,031, 551. Okay. So we can get the displacement vector. So this is the vector across which the ship has traveled in this 10-second period. Okay. So the new position. What did the question ask for? What will be the position? Well, the position is whatever its initial position was plus s. Okay. So the final position of the ship. Final position will be equal to whatever initial position it had plus this s. Okay, because that s is the displacement. Difference between its initial position and its final position. We're also asked for the ending velocity. Well, we've got initial velocity and acceleration, so the final velocity v at the end of the 10-second period then given by v will be the initial velocity plus acceleration times time. Okay. We know the initial velocity, we've got our acceleration vector, and we know t is 10 seconds. So this will come out as, so it's 100 is the v, acceleration is this 0.6, so on, 1.0, so on, minus 0.35, and so on. And this time we're multiplying that by 10. So this is approximately 106, 60, and 6. Just approximately. Okay, but that's just there to illustrate the use of force, or how we might admit the force vector into these descriptions. Okay, but what we really want to get onto then is that final section 8.9 on momentum and energy. And we're looking here at some physical principles, some principles from physics. We're not going to investigate we're not going to really investigate the physical theory underlying them, but rather take these principles from physics and show how they can be applied to various mechanics type problems and give you some quite, some quite nice ways to get solutions out to mechanics problems. You can see the solutions quite nicely from just applying some basic conservation rules. Okay. So we're going to look at momentum and energy and their conservation rules. Okay. So what is momentum? Well, the concept of momentum is the product of mass times velocity. So if an object is moving with a certain velocity, it has a certain momentum. Now, if it's just one-dimensional motion, then the momentum would be a scalar quantity. But if you're using a vector description for a movement in 2 or 3 dimensions, then the momentum will become a vector quantity, the scalar product of the mass with the velocity vector. And from physics, we get this important conservation principle that in any closed physical system, so any system where you kind of got the totality of effects going on, or you assume you've got the totality of effects going on, and all the objects that are applying forces to one another, we have this principle that the total momentum is conserved. So this can be important for analyzing collisions, for instance. That the total momentum of the system, so the product, the sum of all the products of velocities and masses of moving objects before the collision, well, the objects collide and then they have new, perhaps they break up, so there's more objects with smaller masses, and objects change direction, maybe change velocities after the collision. So there's new velocities and new masses, potentially, after the collision. But the assumption, or the conservation law, would state that the total momentum of the system can't be changed. The total momentum of the system post-collision should be the same as the total momentum before. Then we have the concept of energy. And energy can come in a variety of forms. Two important ones for us are kinetic energy and potential energy. Kinetic energy is the energy that an object has due to its motion. So, and that's given by this important expression: half times the mass times the magnitude times the square of the magnitude of the velocity equals a half m magnitude of the velocity squared equals a half m speed squared. Okay, so that's the energy that an object possesses due to its motion. There's potential energy as well. So this is the energy that's stored by an object due to its position in some kind of force field. Typically, for our kind of motion of objects under gravity type situation, that's the position of the object in the gravitational field. So the height of the object above, say, some ground, or the height of the object relative to some reference level. So that's called potential energy, because maybe if the object is being supported at a certain height, the energy is stored in the object, and the energy can kind of manifest itself if the object starts to fall under gravity. Where is the energy coming from that's making the object move up? The energy is there as potential energy when the object is at a certain height. And this is quantified as mass times g times the height. Okay, so the mass of the object times the magnitude of the acceleration due to gravity times the height of the object. Then there's other forms which are maybe less relevant for us in this context. There's electrical energy. Heat energy, the energy of an object due to the temperature of the matter in the object. Okay, so that's the total heat energy in an object. You have other kinds of energy as well. And we have an important physical principle of the conservation of energy. Okay? Energy might be transferred or transformed from one form into another. But there's this physical principle which we can apply to our mechanics problems, which says that, well, energy can't be destroyed. It can't be lost from a closed system. As long as you're taking into account all the effects in a system, or you assume that you are, then you can use this conservation of energy principle to solve some problems as well. Okay, so let's take an example problem which illustrates the use of these. And so we're going to consider a roller coaster. Illustrated in here. So the roller coaster starts off at a certain height and it follows the track. What information are we given? We're told that the track begins with a drop from a height of 100 meters. So as you can see in the diagram there, the high point of the track is 100 meters above the ground. And the track goes down to ground level, or close to ground level, and it then rises again to a height of 30 meters. Now, assuming that the track is smooth and effectively friction-free, so here we're assuming that energy is not being transferred into other forms due to friction with the wheels with the track, or friction of the wheels with the axle of the thing. So assuming that no energy or a negligible amount of energy is lost through friction and so on, what speed will the car be traveling at the bottom of the track? And again, after rising to a height of 30 meters. So assume it's starting off as stationary at the top, it speeds up as it's falling down and reaches some kind of maximum speed, but then it has to go up this raise again, and it's going to lose speed due to that, so it's moving against gravity. Okay, so we're asked for its speed to be traveling at the bottom of the drop, so at this ground level down here, and what speed it has at the top of the 30-meter rise. Now, the first interesting thing to note in that question is the question doesn't tell you how massive the cart is, what the mass of the cart is. So it's kind of suggesting that the speed that the cart reaches, both at the bottom and at the top of that, well, the suggestion is that it's independent of the mass. So that's the first interest. So that's the first interesting thing to find out. Okay, so let's have a go at solving this. Exercise 8.8. Okay, so we'll solve this using the conservation of energy. Okay. Conservation of energy. So at time 0, the cart has potential energy because it's at a certain height. We'll assume it's at rest, so it has no kinetic energy, it's not moving. So the only energy the cart has is due to the fact that it's high up in the gravity field. So the cart has potential energy. And its potential energy is mgh. So whatever its mass is. Now we haven't been told its mass, so we'll just keep that as m for the moment. But we're told the height of the track is 100 meters. So this energy that it has is 9.81 times the mass. Units of these energies are joules, but I'm going to neglect that for the moment. That. So time zero is sitting at the top of the track. So at time zero, it's given a little nudge or whatever, or the brake is released. So it begins to fall under the action of gravity. And at some time, it will reach the bottom of the track. It will reach point zero. Okay? So at the bottom of the hill, so height equals zero, it has lost all this potential energy. Okay. It doesn't have any potential energy anymore, or the potential energy it had because it was at height 100 has now all disappeared because it's at height equals zero. Now, the principle of the conservation of energy says that, well, the energy can't just disappear into thin air. We can only change its form. And presuming no energy is going into generating heat through friction or noise through friction, presuming the only place for the energy to go is into the kinetic energy of the object, the energy that the cart has just due to its motion. Okay. So we assume that all of it has been converted, changed into kinetic energy, into the kinetic energy of the cart. So this is equal to half m times the magnitude of the velocity squared, which we'll just write as a half mv squared, since assuming one-dimensional motion. So we get by the principle of conservation of energy, we get that the potential energy 9.81 times this should be 981. Well, I lost my multiplying by 100, didn't I? 9.81. So sorry, this is 981 times m. So 981 times m, yeah, must be equal to my half mv squared. And here we see that feature which we kind of suspected from the way the question was phrased, is that the mass, it disappears. Or this now says that the velocity is going to be given as being independent of the mass. So the velocity actually only depends on the height. Well, the height of 100 meters is contained within this figure of 981. The gravitational acceleration times the height. So we get that v then should be the square root of 2 times 981, which comes out as approximately 44.3 meters per second. So it's interesting that the mass of the cart doesn't seem to influence the velocity that it has at the bottom of the hill under these assumptions. And we get the velocity pretty nicely just by applying this conservation of energy equation. So we aren't getting any information here about the time it takes to get to the bottom. Might depend on the shape of the track. Sure. But we get its velocity at the bottom of the hill pretty nicely. So 44 meters per second is quite fast. I think that's around 100 miles an hour, approximately. This is quite a roller coaster. But what's happening to it when it gets to the top of that 30-meter hill? Okay. So at the top, at the height of 30 meters, it has gained some potential energy. Okay, because it'll now have potential energy of 30 times 9.81. Where does that energy come from? We're assuming that the cart is free running, it's not being driven by any motor or anything. So that energy could only come from the kinetic energy that it has. Okay, so the unaccounted for initial potential energy so when it gets back to a height of 30 meters, it's recovered some of its initial potential energy. But the amount of initial potential energy, which is where all this is coming from, that's unaccounted for then, is equal to the mass times 9.81 times the difference in height, so times 70 meters. So this is 70 times 9.81 times the mass. So all of this potential energy must be embodied in the kinetic energy that it has when it gets to the top of that 30-meter height. Okay? Because we've subtracted the potential energy due to being at a height of 30 meters away from the original potential energy it had. So by the conservation of energy, this must be equal to a half mv squared. So this is using the conservation of energy principle again. With the velocity v, the velocity at height of 30 meters. So again, the m's cancel, and we get here an expression for v. So v is going to be the square root of 2 times 9.81 times 70, which, when you evaluate that, is approximately 37.1 meters per second. So that principle of conservation of energy can be used to work out, velocities achieved from the conversion of potential energy, or perhaps going the other way, it's given a certain amount of initial velocity, what height could it reach using that kinetic energy? Okay, because it would have to convert that kinetic energy into potential energy by getting to a certain height. So you can solve these kind of problems by applying that conservation. So there's another exercise there, 8.9 in the notes, which might lead you to work on yourselves. Then I'd just like to show you an application of the conservation of momentum as well. This is actually combined with the conservation of energy principle. So this application is in a certain type of collision. These are one-dimensional, so-called elastic collisions. It's one-dimensional motion. We're just going to talk about two objects, say, moving towards one another, say, but they don't have to be moving towards one another. Could be both moving in the same direction, but the following one moving faster, so they're going to collide. But the term elastic here would mean that the elastic means that there's no energy lost through deformation of the objects, by no energy used in destructing some of the objects, or heat generation from the collision, or even light generation when you get. You can actually collide objects with very fast or with a lot of energy. You can actually observe light being created, sparks being created when they collide, and so on. But elastic means that we don't have energy lost through any of those kind of things. So maybe so the objects collide and they survive the collision, and of course their velocities are going to be influenced. We're going to assume that the masses remain the same. So the masses remain the same after collision, but the velocities change. The masses remain the same after collision, but the velocities change. And it's going to turn out that those two principles, the conservation of energy principle and the conservation of momentum principle, is enough to tell us the relationship between the initial velocities, or the velocities pre-collision, and the post-collision velocities. Okay, so we've got our two objects with mass m1 and mass m2. So we'll let u1 and u2, in general these might be vector quantities, but because we're just dealing with one-dimensional motion, we can just take them to scalar quantities. We'll let u1 and u2 be the pre-collision velocities, and v1 and v2 be the post-collision velocities. So the objects are moving with constant velocity before they collide, and then their motions will be changed, and they'll have new velocities, v1 and v2. These are the post-collision velocities. So what we seek here, or the solution we're looking for, what we're seeking is v1 as some function f of u1 and u2, maybe the masses m1 and m2. Call that an f1, and v2 to be some other function of, it's probably not quite similar, but some other function of the data. Because there's no energy being lost into these other forms, it's just affecting the velocities of the objects, the conservation of momentum and kinetic energy principles will be enough to get this for us. So we'll use the conservation of kinetic energy and momentum principles. Conservation of kinetic energy and momentum loss. So if we look at the kinetic energy, before and after. Well, the total kinetic energy before will be a half m1 v1 squared plus a half m2 v2 squared. Sorry, before we'll be using the u. So, sorry, the kinetic energy, the first object before the collision is a half mu1 squared. The second object is a half mu2 squared. And post-collision, their kinetic energies are a half mv1 squared and a half mv2 squared. Now we can disregard the half, so we can multiply across by 2, and say that the total kinetic energy before the collision, which is m1 u1 squared, or half times this, if you like, m2 u2 squared, this should be equal to the total kinetic energy after the collision, which is m1 v1 squared plus m2 v2 squared. If we assume the pre-collision velocities would be different to the post-collision velocities, okay? Because the objects might bounce off each other. So strictly speaking, there should be a half in front of everything here because we're talking about kinetic energy, but just simplify by multiplying the whole equation across by 2, just to get rid of the halves. And the momentum equation is similar, but without the squares, okay? Because the momentum pre-collision is m1 u1 plus m2 u2. Post-collision, the total momentum is m1 v1 plus m2 v2. Okay, and that must be conserved. Now here we've got two equations, and we're trying to write v1 in terms of the other variables and v2 in terms of the other variables. So because we've got two equations, we hope to be able to do that. But now we can use a simplifying. It's a little bit complex at the moment. So what we'd like to do is simplify this picture. And I'm going to relativize to one of the objects. See, at the moment, because I'm considering the velocities of the two objects, I'm kind of considering a fixed origin somewhere. But instead, I can make the origin move with one of the objects. So these four velocities, u1, u2, v1, v2, I can instead adopt a moving frame of reference to make one of those four velocities zero. So we'll simplify and we'll move the origin. Move the origin with velocity u2. So effectively replacing the origin on the second object pre-collision, or assume u2 equals 0. Okay. Now that's going to simplify these equations. We'll undo this simplification at the end. Okay. So we can just relativize everything to the movement of the object to pre-collision. So that would tell us that m1 u1 squared is m1 v1 squared plus m2 v2 squared. So we're not assuming v2 is 0. We're assuming here the second object is at rest. In effect, the first object is moving along, it's going to collide with it. So after collision, both the objects are going to be moving. Probably. And then the momentum equation will be m1 u1 equals m1 v1 plus m2 v2. Okay, and I can call these equations A and B. So I've got my conservation of kinetic energy equation is equation A, and then the conservation of momentum equation is equation B. Now these aren't linear equations. If they were linear equations, you just solve them by Gaussian elimination, and they're not linear, but they're not too non-linear. They're just one of them is quite quadratic. So with a little bit of careful manipulation, we should be able to solve this. So we can take equation B. So from B, we're going to write V1 in terms of the other variables. Okay? Because ultimately we want to express V1 in terms of the other variables. But for the moment, it's going to use, it's going to have to use V2 as well. So it's going to be U1 minus M2 over M1 V2. So I'm going to make V1 the subject of V. So I put everything over the other side and divide both sides by M1. So we get V1 equal to this. So this is moving towards what I want my conclusion for V1 to be. But I don't want the new velocity V2 to appear over here. I just want to express V1 in terms of the old information. The masses M1 and M2, and the old velocities U1 and U2. So I'll place this into A. So I've taken this information from equation B, so I should place it into the other equation. So this would give me now M1 U1 squared on the left. I'm replacing for V1. So I've got M1 times square of all this, which is U1 minus M2 M1 2 squared, and then I've still got my M2 V2 squared. Well, I'll just keep going with this. So I've got M1 U1 squared on the left, and let's square out this bracket here. So I'll have M1 U1 squared on the right. And then I'm going to get an M2. Let's leave the M1 outside the bracket. So we've got M2 squared over M1 squared V2 squared. And then the cross product term minus 2 M2 over M1 U1 V2. That's what I get from squaring out the bracket. And then I've still got my M2 V2 squared at the end. Remember what have I done? I took my conservation equation and substituted it into the kinetic energy equation. But then you can see we're going to get some simplification here. You got an M1 U1 squared on the left, and we got it on the right as well. So they're going to cancel out. That's really nice. And multiplying this M1 here, well, you can see you've got M1s in the denominators here. You'll be able to simplify those out as well. And at 0, we can cancel the M1 U1 squared. So we're going to have 0 on the left. Multiply in the M1, so we'll have M2 squared over M1 V2 squared minus 2M2 U1 V2, then plus the M2 V2 squared that I've got at the end still. Now this is looking yeah, common factor. We've got common factor V2 and everything. So you can divide out by V2. We got 0 is M2 squared M1. In fact, M2 V2 is a common factor. So I should divide that by M2 V2. So I get M2 over M1 V2 minus 2 U1 plus V2. So then you just want to make V2 the subject of this, which you can do by saying this is then 2U1 is M2 V2 over M1 plus V2, and then multiply across by M1, you get 2U1 M1 equals M2 V2 plus M1 V2. So finally, you get this expression now. V2 is 2U1 M1 over M1 plus M2. Now this is the form of the relationship that I declared we were seeking in the beginning. Here I have the new velocity V2, now just expressed in terms of, well, the masses M1 and M2 and one of the pre-collision velocities, U1. And a while ago, up here in the box at the top, a while ago we passed through this equation here, which related V1 to U1 and V2. But we now have V2 in terms of old information, in terms of the U1 there. So we can substitute that back into that previous equation. So maybe I'll label this equation up here as C. So this was the one we got by making V1 the subject of B. That equation C. We'll call this equation here D. Now by substituting D into C, substitute D into C to get a nice equation for V1. You're going to get V1 was equal to U1 minus M2 over M1 times V2. But now V2 we've got is 2 U1 M1 plus M2. So that tidies up to give you V1 times U1 minus 2 U1 M2 into M1 plus M2. We call that equation E. So then we've got these two equations, D and E, which give us this nice relationship. The new velocities V1 and V2 in terms of the masses and the old velocity V1. Now remember, all of this, we simplified the situation by relativizing to the second object, to the U2. Remember, we set U2 equal to 0 in the beginning. That's eliminated one of the variables and allowed us to make some progress with the equation. But we can undo that now by so how did we make U2 0? We made U2 0 by subtracting U2 from all the velocities. So now we just have to add it in again. Okay. So we add it back now to all the velocities, and that should give us the general solution. So all the velocity terms we see here, we'll now replace them with themselves plus U2. So when you take equation D there, on the left-hand side, you now have V2 plus U2. And this is equal to 2 times U1, but I now have to replace U1 with U1 plus U2. And this is still multiplying M1 over the sum of the masses, M1 plus M2. So you get this equation and the equation from E, which is V1 plus U2 is U1 plus U2 minus 2 times, and again, instead of U1, I've got U1 plus U2, and this is now multiplying M2 over M1 plus M2. But then the U2s can simply move to the other side. We can get rid of them, and we can again recover the form of equations that we want, which is V1 and V2 in terms of the old information. So these can, I mean, I won't go through all the steps, but these can be tidied up just using basic algebra, tidied up to give what are called in a sense, the velocity solution equations for one-dimensional elastic collisions. Get an equation which is V2, which is it's a combination of U2 and U1. And it's 1 minus 2m1 over m1 plus m2 times U2 plus 2m1 over m1 plus m2 U1. We've got this nice symmetric form. So V2 is if you like, a linear combination of U2 and U1, and the coefficients sum to 1. And they have this form 1 minus 2m1 over m1 plus m2. And then by symmetry of the whole thing, you can kind of guess what the equation should be for the second one. You just reverse the behavior, or interchange the behavior of object 1 and object 2. Let's get 1 minus 2m2 over m1 plus m2, and this multiplies u1 now, and then you have 2m2 over m1 plus m2 times u2. So this is post-collision velocities in terms of pre-collision velocities. They're nice expressions. Post-collision velocity is a linear combination of the two pre-collision velocities, and it's very nice kind of form. The coefficients in the linear combination, they add to 1 in both cases, and the coefficient, the 2m2 over m1 plus m2, the 2m1 over m1 plus m2, this nice symmetric. So I think that's where we're going to finish on there. That kind of nicely illustrates the application of some of those properties. It shows their utility.